Hello, everyone, and welcome to TL Eliminators post contest discussions. Today, we'll be discussing the Codeforces Educational Round 182. How was the contest, guys? How many questions did you guys solve? Why is A harder than B? Yeah, to be honest, A is a bit number theory knowledge. I found B much more straightforward. Um, but then A you could have easily brute forced as well. So, yeah, we'll get in the questions soon. How was the contest? All? What does all mean, Jatin? Decent contest, I would say. Although I had a lot of interruptions in between, so I didn't perform as good as I thought, and I didn't get even. But yeah, so all three didn't get how to get X and D. Yeah, B was quite easy. B was quite easy. Yeah. All right, then, guys, we'll get into the discussion soon. But before we start our discussion, I would like to announce that our flagship courses of TL Eliminators are live. So we have self-paced courses for competitive programming divided across four different levels, all the way from level one, which starts with complete beginners who are completely starting their coding journey. So it teaches them C++ syntax, it teaches them basic maths, what are time and space complexity, how to sort strings, debugging, stuff like that, all the way to level 4 where you get into advanced concepts like dynamic programming, generic trees, graphs, disjoint set union, segment trees, etc., etc. So based on your current comfortable, like your level of comfort and your your decision on what topics you know and what topics you don't know, you can go ahead and check out the course. The courses are super affordable, or just a few thousand rupees. So the return on investment for this is very high, and each course has more than 40 hours of recorded lectures, more than 100 practice problems in each level, right? And there are hints and video solutions for all the problems, as well as doubt support available almost all times of the day. And the doubt support within 10 minutes. If you have any doubt, whether it's from the course, outside the course, you can ask a question and a mentor will pick it and answer it for you. All right, so that's about the eliminators. We'll get into the contest discussion. um Completed level 4 today. Awesome course, I would say. Thank you very much, Jatin. So yeah, as you can see, we have a lot of students also who find the course pretty nice. Yes. Any good resource to learn DP? So obviously the Eliminators course. But if you cannot do that, then do try the Competitive Programmers Handbook, which is available online. Okay. Was able to solve only A. Was able to solve A and B, A, B, C. Nice. So most people seem to have solved A, B, or A, B, C, right? Okay. I see. There are a lot of people who solved A only, which is surprising to me, seeing that B was not that hard. But okay, we will spend some time on B as well. Okay, so let's get started. I would say it was a pretty nice contest today. Let's get started with the problem A. Okay, so problem A goes, cut the array. You are given an array of n non-negative integers, ai to an. Your task is to cut this array into three parts: one prefix part, one middle part, and a suffix part. And basically, here's a formal definition, but I guess you all understand. We need to cut it into three parts: one prefix, one middle, and one suffix, right? So basically, we need to find L and R positions such that we can cut it into the prefix, middle, and suffix. N goes up to 40, A of I goes up to 40, and our task is to find some L and R such that the sum of these parts modulo 3, right? So S1 equals sum of this part modulo 3, S2 equals sum of this middle part modulo 3, and S3 equals sum of suffix part modulo 3. All these parts should either all be different or all be same. Okay, so either these are all different or all the same. And if such lnr exist, then we can print it. If none such lnr exists, then we can output 0 0. Okay, so I will discuss two ways I will discuss two ways of solving this problem. One is the brute force method, which is the one which I did in contest. The second is the elegant and simple number theory method, which also is some people have done in contest, but yeah, it's not that easy to think of, at least for me. So let's get into problem A. So our first observation is that the constraints are very low, right? So we can write observation 1 directly as constraints are very low, right? So we can see that n goes up to 40, so n is less than equal to 40. So therefore, even n cubed or big of n for brute force solutions will pass, right? If we just choose our L and R, then find the sum via brute force, and then we check if any LNR satisfy the given conditions, correct? So even n cubed or even up to n to the power 4 also brute force solutions can pass for this, right? So our first solution is simply do a brute force, simply do a brute force, do a brute force, and we can iterate over all possible values of LNR, iterate over all possible values of LNR, values of L comma R, right? So we are given our given array, and we have to make sure that the sum of the first half and sum of the middle half and sum of the right half, if you take mod 3, they're either all different or all same, right? So let's say we chose some L while brute forcing, we chose some R while brute forcing, then we know the sum of this, right? We'll call this S1. We know the sum of this, we'll call this S2, and this can be calculated while doing our brute force itself. And now if we want S3 will be just the total sum minus S1 minus S2. Okay, so S3 is simply the total sum minus S1 minus S2, right? So now all we need to do is, if um, S1 mod 3 is equal to S2 mod 3 is equal to S3 mod 3, right? S3, right? And if this holds, then all we need to do is, we can output the values of LNR, output the value of LNR and return, right? Similarly, if S1 mod 3 is not equal to S2 mod 3, and this one is also not equal to S3 mod 3, again we can output LNR and return, LNR and return, right? Otherwise, if no values of LNR work, if no values work, if no values work, then we can return 0 0, right? Or we can output 0 0 and return, right? So this is the direct brute force approach, and it becomes mostly like a typing speed test to see who can do this fastest, right? uh, yeah, okay, so this much is understandable, right? We can use prefix sum for A. Obviously you can do many ways to do A, right? And we will get to the number theory solution soon. Let's just see the code with brute force. Let's just see the code with brute force. So yeah, so I used a solve function so we can return easily at any point. Now what I'm doing is, so yeah, the code is a bit ugly because I typed it in a hurry, right? In a contest you're in a hurry, so the code isn't that clean, please bear with me. So yeah, what I'm doing is I'm taking the input n, and I'm taking the input of elements, and I'm also calculating sum of all elements in this sum variable. Okay, now for each possible L, so j is all the possible L's, possible L values. Okay, so for each possible L value, I'm finding the sum S1, find S1, right? Find the sum S1. Now I'm going to find all R values, all R values, and here I'm calculating S2, right? I'm just directly calculating the value of S2, and then I'm checking if the first condition satisfies. S1 mod 3 is equal to S2 mod 3, and the S2 mod 3 is equal to S3 mod 3, right? This is S3. This value is S3. Similarly, I'm checking if they're all unequal, and if any of these cases hold, then I can output LNR, right? Output LNR. In my code, L is equal to J and R is equal to Y plus 1. You can verify this. Because I was in a hurry, I didn't quite name the variables very neatly, but that's what this code does, right? So just go through the code. Obviously, you can write the brute force in many ways, and maybe a neater way to write the brute force will also be there. Okay, right. There is a much more optimal solution. Big O of n solution. Actually, big O of one solution is there for this problem. So yeah, I'll just tell you that. Okay. So now we'll get to the number theory solution. Everyone understood the brute force solution. Brute function which I told has a time complexity of big O of n squared. Okay. Time complexity of brute force is big O of n squared. Okay. Now let's get into the optimal solution or number theory solution. Uh, number theory solution. Okay. So in the number theory solution, um, the main thing we need to pay attention to is two observations. Okay. So the first observation is that examine the given conditions. Okay. Examine the given condition, right? And what is the given condition? The condition says that if we are given this array and we divide it into S1, S2, S3, right? So in one of the cases, we are saying that S1 mod 3 is equal to S2 mod 3 is equal to S3 mod 3. Okay. So in this condition, what happens is that let's say S1 was equal to 0, right? Mod 3. Obviously, everything I'm considering mod 3. If S1 was divisible by 3 and S2 equals 0 mod 3, right? And S3 equals 0 mod 3. So all are equal, right? Then in this case, the sum S1 plus S2 plus S3 is also equal to 3 mod is equal to 0 mod 3, right? Similarly, similarly, for any values of for any value of S1, or I can write this in a neater way. I can say that if S1 mod 3 and S2 mod 3 and S3 mod 3 are all equal, then what would happen to S1 plus S2 plus S3 mod 3, right? So let this be equal to X. Okay, so let this be equal to X. Then what we would get is basically we would get 3x mod 3, right? So that would be equal to 0 mod 3, right? So basically, if this condition holds, if condition 1 holds, then the whole array is 0 mod 3. Okay. So what about condition 2? So this is for condition 1. What about condition 2? Now, if for condition 2, if you observe that, we see that S1, S2, and S3, they all have different values mod 3, right? So maybe one of them will be 0, one of them will be 1, and one of them will be 2 mod 3, right? Because those are the only values possible mod 3. So basically, the sum of S1 plus S2 plus S3 mod 3 will be equal to 0 plus 1 plus 2 mod 3, right? Which will be equal to 0 mod 3. So basically, both the conditions, if they need to hold, for both the conditions, to hold, we need the sum of all elements to be divisible by 3, to be divisible by 3. Okay, so this is the first condition, guys. For the condition to hold, we need the sum of all elements to be divisible by 3. Okay, so we can get some pseudocode like this. We have our vector a, and we can input all the values of the vector. So we see in this value, and what we can do is sum will be added with this value, right? Now if the sum mod 3, if sum mod 3 is not equal to 0, then there will be no solution. Okay, if the sum mod 3 is not equal to 0, there will be no solution, and we can simply see out 0 0 and return. Okay, we can see out 0 0 and return. Fine. Now what about the other case? In the case that yes, the sum is divisible by 3, then what happens? Then there is a very interesting fact we can prove. We can show that if the sum is divisible by 3, if sum is divisible by 3, then any partition, then any partition is correct. Okay, then any partition will be correct. And why is that? Why is any partition always giving us the answer? And I'll show you that. Okay, so let's say if the whole total sum s is divisible by 3. Okay, total sum s is divisible by 3, so total sum s is congruent to 0 mod 3. Then we have s1 s2 s3. Right, so if s1 is equal to 0, right, then s2 will, let's say s2 is equal to 0, then in this case what happens? S3 is also forced to be 0, because then the total sum has to be 0 mod 3, right? Since the total sum has to be divisible by 3, then this will be also forced to be 0. Now similarly, let's say if s1 was equal to 1 and s2 was also equal to 1, then again s3 will be forced to be equal to 1, right? And similarly for all the cases like that. Now what if s1 was equal to 0 and s2 was equal to 1, let's say? Then again s2 will be forced to be equal to 2, right? So basically what is happening is, if the whole sum is divisible by 3, then for any partition, whatever we choose as s1 and s2, s3 becomes forced to be the corresponding value, which makes the whole thing divisible by 3, right? Which makes the whole thing divisible by 3. So if you choose s1 as 0 mod 3, s2 as 2 mod 3, then s3 will become 1 mod 3, right? So it basically becomes the missing one, so that the whole thing sum becomes equal to 0 mod 3. Right, so if the whole sum is divisible by 3, then any partition is correct. So now we can finish the code and we can print any partition, right? So we'll take the first element as the first part and the second element as the second part, and then the remaining elements can be the third part, right? So we can just simply write, the final code. Else we can simply see out 1 2 slash n, right? And then we are done. So that's all for this question. If we use number theory, we get this very clean solution, right? And I'll just code it up, because I haven't coded this up yet. But yeah, I saw a GM doing the same code and I realized it myself as well. So yeah, all you need to do here is just we just need the sum. So if sum is not equal to, sum mod 3 is not equal to 0, then we do this. Otherwise we can output 1 2 slash n. So this is the solution using number theory. Okay, much shorter, and we don't need to brute force. And the solution, if you disregard taking the input, then the solution is basically big O of 1 itself. Okay, so are people clear with this, guys? Overall contest review, I would say moderate. There were a lot of questions which looked like they require advanced concept, but they actually were some simple concept itself. C can be solved with DP, but you can solve without DP as well. I saw someone get this solution within 1 minute. Some GM got this number 3 solution within 1 minute. So yeah. Okay, so I'll move on to problem B now. I hope everyone is clear with both the solutions of problem A. Let me just note down the time complexity for this. So the time complexity here is big O of n for input. Basically, just to read input, it's becoming big O of n. No other reason. Problem B. Okay, so let's go ahead and read the problem B. Recall that a permutation of length n is a sequence of length n such that every integer from 1 to n appears exactly once. Let's define the cost of this permutation as the minimum length that of a subarray which needs to be sorted so that the entire permutation becomes in ascending order. Okay, so basically we need to find the minimum length subarray to sort so that the entire permutation becomes ascending order or increasing order. Okay, you're given an array P which consists of some permutation, and some values of the permutation are 0, which means they are missing values. Okay, so basically we're given a permutation as input and some values are 0, that means that they are missing values, and we need to find the maximum possible cost of this permutation. Okay, we need to find the maximum possible cost of the permutation. For example, see here we have 1 0. Basically this is a permutation, like 1 is over here, 4 is over here, and 5 is over here, but these two values are missing values, and we can fill them with the remaining values in any way that we want. Okay, so we can fill them with the remaining values in any way that we want, right? Yeah, yeah. So here the approach is basically yeah, so first let's just take a look at the constraints. So t goes up to 10 power 4, n goes up to 10 power 5, sum of n also goes up to 10 power 5, right? So normal constraints, very ordinary constraints. N goes up to 10 power 5 power 5. So big O of n log n or big O of n solutions are typical, right? Are expected. Big O of n square obviously will not work. Okay, so what do we need to do here? Right, so first of all let's try to find out what is the longest permutation or minimum, what is the minimum length of the subarray which needs to be sorted. Okay, so let's say there are no missing values. Let's simplify the problem. Simplify the problem. Let's say there are no missing values. Okay, let's say there are no missing values. There are no missing values. No missing values. Then what is the minimum subarray? Then what is the minimum subarray? Minimum subarray. We need to sort. We need to sort so that the whole permutation is sorted. Okay, so that the whole permutation gets sorted, right? Is sorted. So for that, let's take an example permutation and a reference also. So let's say a permutation is 1 2 4 3 7 6 8 5 10 9. Okay, so let's say this is a permutation, and then what do we want it to be? We want it to be perfectly sorted, right? So we want it to be equal to something like this: 1 2 3 4 5 6 7 8 9 10, right? We want this to be our target. So now what is the subarray that we need to sort? Okay, what is the subarray that we need to sort? And then there should be a direct observation. Direct observation. Direct observation. Every element where a of I is not equal to the target value of at that position. Okay, target value at I should be sorted, right? Every value which is not equal to the target value, that value has to be sorted, right? So for example, a value like that is this, here, 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 here. So all these values must be affected by the subarray sorting, right? All these values have to be affected by the subarray sorting. So that's why the subarray has to be the leftmost of these values till the rightmost of these values. So this is the minimum subarray we need to sort the whole list, right? Minimum subarray, correct? So this is the minimum subarray we need to sort so that the whole permutation gets sorted. And basically we just need to check which is the first value of a of I not equal to target, which is the last value of a of I not equal to target. Okay, so basically um, let us write it like this: let L equal to first value I such that a of I is not equal to I plus 1, right? R be equal to first value of I such that a of I is not equal to I plus 1. Sorry, it should be last value. R should be the last value such that a of I is not equal to I plus 1. Okay, so that's the length of the, this will define the length of the minimum subarray, right? So this will be L and this will be our R, and the distance between them will be the length of the subarray. So observe that distance between them, length of min subarray to sort, that will be equal to R minus L plus 1. Okay, R minus L plus 1. So this is the length which we need to sort. All right, so we have solved the case where there are no missing values. Then we simply need to find the first value such that a of I is not equal to I plus 1. Last value such that a of I is not equal to I plus 1. And then we get the length of the subarray, right? We get the length of the subarray. Now what if this subarray had missing values? Okay, let's now consider the case with missing values. Now consider the case with missing values. Okay, so now for that, let's say we have 1 2 0 0 5 6 7 0 9 0 10 11. Okay, so let's say this is our missing case. Now here what we need to do is we need to figure out how to fill the missing values to maximize our answer, right? And we know our answer depends on two things. It depends on the value of L where the first position a of I is not equal to I, also R where is the last position a of I not equal to I. Okay, so what we can do is whichever the leftmost zero is and whichever the rightmost value of R is, we will choose those two. We'll choose those two, and we can fill some values which are incorrect, right? We can fill some values which are incorrect. For example, we can fill a value of 4 over here, and here we can fill a value of 8, right? The other values don't matter. We can fill whatever we want, like we can fill 3 here, and we can fill 8 9, we can fill 12 here, something like this, right? Sorry, not 12. So let's say, okay, so my example was a bit off from what I was trying to show, but yeah, 11 12. Okay, so we can fill 10 over here. Okay, so it doesn't really matter as long as the first position where we got the 0, there a of I is not equal to I. Similarly, the last position where we got a 0, there the a of I is not equal to I. Okay, so as long as we can ensure this, we can make it happen. And yeah, that's about all we need, right? And so one of the ways to do it, and this is the way I did, this is the way a lot of people did, for all the missing values, just fill them in descending order. Okay, just fill them in descending order, and this ensures that always, if it's possible, for the first a of I not to be equal to I, it happens. For the last a of I not equal to I, that happens. So fill them, just fill them in descending order. Okay, in descending order. So what would that mean? In this example, it would mean that the missing values are 3, 4, 8, 10, right? These are the missing values. So what we'll do is we'll fill 10 here, we'll fill 8 here, 4 here, and 3 here, right? So in that way, these values will be filled in descending order, or they will be um, the first value of a5 won't be equal to I, and the last value of a5 won't be equal to I. In fact, even if you did not know this logic, it's very simple to guess that you should fill them in descending order, because like in intuitive or guess method, like a very guessy method which you can do in a real contest and not prove, is that if you fill in descending order, you're like maximizing the unsortedness, right? You're maximizing the unsortedness of the array. You're kind of, in a sense, maximizes the unsortedness. Obviously this is not a formal proof, but if you had a gut feeling like this, you would have done it, right? Unsortedness of the array. Okay, so all the missing values will just fill in descending order, and this ensures our condition without much thought. It ensures that the first value of L will have a of I not equal to I, the last value of 0 will have a of I not equal to I, right? And then all we need to do is do the previous thing again. Find the first value of L such that a of I is not equal to I, last value of R such that a of I is not equal to I, and print that distance between them. Okay, so let's do a summary, and the summary is going to be like this: fill the missing values in descending order, fill the missing values in descending order, then find L and R, that is first and last position, such that a of I is not equal to I, and then our answer will simply be R minus L plus 1, right? So that's our answer, and this value is big O of n log n, because we need to sort it in descending order, or we need to store in set or something like that. So obviously n log n. This is big O of n. This is also big O of n. So the overall time complexity of this will be big O of n. Although you can use these observations to solve it in big O of n, because we're doing sorting here, it will be big O of n log n. All right. So time complexity is big O of n log n for this solution. But yeah, you can optimize it. You don't actually need to sort in descending order. You just care about the first values of zeros, right? So in that case, you can solve it in big O of n as well. But in a contest, as long as your solution is good enough, all you need to care about is whether it's simple to implement or not, right? You don't need to unnecessarily try to optimize. So that's why I went with the n log n solution. Okay. So is this explanation clear, guys? Yeah, fill the zeros in descending order, pretty much correct. Do you think the expert should be able to solve up till D or not? Depends. D was a bit tricky today, so maybe not. Can a newbie do C? Yeah, it is possible. If you're good at math, you can do C. I mean, yeah, true. It's not normal for a newbie to do C, but then the thing is, nowadays there's a lot of rating inflation, kind of. So there are a lot of people who are newbie, but they might have skills of, like a pupilish level. So yeah, true. Yeah, technically you just need the index of first and last position where a of I is not equal to I. So that is all you need actually. But yeah, let me just show you the solution which I wrote. So this is the solution which I wrote. So I take in n and I have all the numbers from 1 to n in a set. Okay, I have all the numbers from 1 to n in a set. For each element, I take input of that element, and if it's not 0, I erase it from my set. Okay, so S holds all my missing values. S holds all the missing values. Okay, all elements which do not appear in V. Okay, right. Now for each element of V, if it's a 0, so if it's a 0, I will fill it with the last element of my set. Okay, so for each element, I'm filling in descending order. Okay, so I'm filling the zeros in descending order. Descending order. Okay. Now, once I have done that, all I need to do is I just need to find the first position such that v of I is not equal to I plus 1, and the last position such that v of I is not equal to I plus 1, right? So, last position satisfying this, and this will be the first position satisfying this. Finally, at the very end, all I need to do is print r minus l plus 1 for the length of that. And I know that because I filled in descending order, I will get the maximum case of this minimum subarray, right? So that's all is the code for this. Obviously, you cannot write the set stuff. You can just find the first position of 0, last position of 0, and also first position vi is not equal to I, and last position vi is not equal to I. So you can do it that way as well, but there will be like 2-3 cases in that. So yeah, this is the solution for B. I hope everyone understood this. If anyone has a doubt, please put it in the chat. No doubts? Okay, then let's move on to problem C. And I guess a lot of people got stuck here. But yeah, it is actually pretty simple. Okay, it's actually pretty simple. If you make one or two observations regarding the input. Okay, so let's go on to problem C. And although this can be solved with DP, I will not tell the DP solution because it is more complicated and not really required over here. But yes, the DP solution is also pretty simple for this problem. Okay, so problem C is non-descending subarrays. We can choose any subset of indices and swap the elements at those positions. Okay, so we can make a swap of AI BI for each I in the subset. A subset of indices is considered good if after the swapping both arrays are sorted in non-descending order. Your task is to calculate the number of good subsets. Since the answer can be large, print it modulo 9982, whatever modulo they've given, right? N goes up to 100, so n goes up to 100. So even n cube solutions are possible, and AI goes up to 1000, BI goes up to 1000. Now I'm not sure why they have given n goes up to 100, because I don't know what the brute force solution is. But this problem can be easily solved in big O of n. And additional constraint on the input, there is at least one good subset. Okay, and I think they should have written this in bold, because this is the main thing which helps you solve the problem, that there is at least one good subset. Okay, and if you think about the condition that there is one good subset, it does teach you a lot. Okay, I want the topic of D is maths and prefix sums. Vishal Agarwal. I see. C can be solved using n cube DP. That's pretty interesting. I do not know that. I also thought of an n O of n DP, but I did not implement it because I found a much simpler solution. Anyways, let's do problem C. Right. So I'll get to the main observations for this. So first we need to understand what the series can look like, right? So let's say we have the example of 2 1 1 3 4 2, right? Now what I can do, what I'm allowed to do is basically, so this is my array A and this is my array B, right? And the only things I'm allowed to do is to swap these, or swap these, so that, so I'm allowed to swap these so that a of I is less than a of I plus 1 less than a of I plus 2. Basically a of I becomes sorted, right? A of I becomes sorted. Similarly b of I also becomes sorted, right? b1 less than b2 less than b3, a1 less than equal to a2 less than equal to a3, right? And this is my goal basically right now. Now the interesting thing is, we already know that there is at least one solution, right? So for example, here we have 2 1, and then here we have 1 3 1 4, which is out of order. This is not sorted, and the other one is also not sorted, right? Not sorted. And right now this is also not sorted, right? But the given interesting fact is that we know that there is at least one solution, correct? We know that there is at least one solution. We know at least one solution is there. Okay, one solution is there, right? So that means there is some valid series of swaps which definitely ensures that both the arrays are sorted. Okay, so how do we, so we just assume, just bear with me for a minute, and let's try to find that one solution. Okay, let's try to find the one guaranteed solution. Okay, let's try to find that one guaranteed solution, and I'll tell you why we're finding this, because it helps us get the answer pretty quickly. Okay, let us try to find that one guaranteed solution. So basically, what we're going to do is, we'll assume that the a1 series, okay, the a1 series, we want it a1 less than a2 less than a3 less than a4, right? So this is what we want. So what we're going to do is, out of a1 and b1, we'll choose the smaller one, and put that in a1. Okay, so if a1 is smaller than b1, then let it be. Otherwise, if b1 is smaller, then we will swap. Okay, so we'll keep a1 as always the smaller series. Okay, so let's assume that a1, let's keep a1 as always the smaller series. Okay, always the smaller series, series compared to bi, compared to bi. Okay, so a1 will be smaller than b1, a2 will be smaller than b2, and so on. And we can show that if there is one solution, then this must be the solution. Okay, if there is exactly one solution, if at least one solution exists, at least one solution exists, then this must be the solution. Okay, then this must be the solution. Okay, must be the solution. And yeah, and why is that? Let's say here we want a to be the smaller series, right? So we'll swap it and we'll get 1 2. Okay, we'll get 1 2. Now the next one is 1 3. So 1 is already smaller, so we'll just keep it as 1 3, right? And the next one over here we have 4 2, so we'll swap it and we'll get 2 4. As you can see, both are now in sorted order, right? Both are now in sorted order. And why am I saying that ai should always be smaller than bi, and that this will be one solution? The reason is that the reason for that is very simple. First of all, a solution is guaranteed, right? And let's say one of these two is the smaller one, right? So for the first element, one of these two has to be the smaller one. So whichever is the smaller one, I'll put that here, right? So let ai be the smaller one, smaller one. So let's say ai is set to the min of a1 and b1, right? So a1 is set to the min of a1 and b1. Then what are our possible options for a2, right? Options for a2, options for a2. And basically the best option is to choose the minimum again. Why is the best option to choose the minimum again? It's simple, because we know that b1 will be larger than a1, right? b1 will be larger than a1, and then we want b2 to be larger than b1, which is larger than a1, right? We want this to happen. b2 should be larger than b1, so it should be larger than a1 as well. So the easiest way is to choose the larger one of them, right? So b1 will be larger of a2 and b2, and sorry, b2 will be larger of a2 and b2, right? So that's why this greedy method. So I hope you can think about it. It's a bit hard to explain, but that's why the greedy method, the greedy method of taking the smaller, of taking the smaller for ai and larger for bi gives a valid solution. Okay, gives one valid solution, right? Because at each stage, if for a we are choosing the smaller one, like the first element, if we chose the smaller one, then the next element also is better if we chose the smaller one. Because if we take the larger one, then this one might become too small. Okay, might become too small, right? If we chose a1 as the smaller one, then we have to choose a2 as the smaller one as well. Otherwise b2 might become very small, right? So that's why we are choosing a2 as the smaller one. Then again we'll choose a3 as the smaller one, then a4 as the smaller one, so on, right? That's why one solution, if it exists, has to be a1, a2, a3, where they are the smaller one of b1, b2, b3. So I hope this one is clear. Is this clear, guys? Maybe because the testing and all is going on, sometimes the server does not work properly. Could just be an internet issue as well. So this much I hope is clear, that if there is a solution, then this one solution is that just keeping the smaller ones in A and the larger options in B. Okay, so now what does this tell us? Okay, what do we do next? Okay, so we have found one solution. Do we do next? And let me just show you this test case. So this test case is the same. Like as you can see, A is bigger over here and B is smaller, so it's very similar. Just A and B are flipped. Okay, so let's say, yeah. So one more thing, one more observation. Uh, observation two is that if A1, A2, A3, AN, and B1, B2, B3, AN, B3, AN, BN is a solution, then if we swap all of them, okay, if we swap all of them, all of them, we get another solution. Okay, we get another solution. We get another solution if we just swap all of them, right? So then we get B1, B2, B3 in top, and A1, A2, A3 on bottom, right? And that also is a valid solution for us to get. So just swapping all of them gets another solution. So basically we have shown that always there will be two or greater than two solutions. Always greater than equal to two solutions. Okay. So we have shown this, right? So for example, that's why you can see the first example has two solutions. This also has two solutions because you can swap them both, right? Now let's go to the third example, where most of our work is done. Like they have made this one as the larger ones and this one as the smaller ones, right? So let's just write that example 3, and we'll try to make some observations from this example. Okay, so let's just write it 2 3 3 4 4. So as you can see, these are the larger ones. Similarly, we have 1 1 3 5 6. Okay, so now the interesting thing is, where and all can we do swaps? Okay, so this is one guaranteed solution, but where can we do swaps? Let's find out. So the first question is, can we swap 2 and 1 in the first position, right? Can we swap 2 and 1? And what happens is we get 1 2 like this, right? And we see that this swap is not possible, because while this part is correct, this part is okay, this part starts violating it, right? This part starts violating it, and the reason is simple. The reason is that for the swap to be viable, we need that the minimum value over here, so min of a1 b1 or ai bi should be, sorry, the maximum value over here should be less than or equal to minimum of ai plus 1 bi plus 1. Okay, then and only then the swap will be possible. Like as you can see, the max value over here is 2, right? The max value over here is 2, min value over here is 1. So this is the min over here, this is the max over here, right? The greater one and the smaller one. Now if we swap this, the greater one will dwarf the smaller one, right? The greater one will dwarf the smaller one like this, right? So then this will become unsorted. This becomes unsorted. So this swap is not allowed. So swapping here is not allowed. Okay, so we can say that swapping here is not allowed. Cannot swap here. Now what about swapping this 3, this 1 and 3? Okay, so what happens if we swap 1 and 3? Well, first of all, this thing becomes broken, right? This thing becomes broken, so we can't just swap 1 and 3 randomly. We need to fix this as well. So to fix this, we will just swap this as well. Okay, so what if we swap this prefix? What if we swap this prefix? And then in this case, this swap is valid. Why is this swap valid? This swap is valid because still 3 is less than 3, less than equal to 3, and here 1 is less than equal to 3. So basically what we got is, in this case, max of a2 and b2 was less than equal to min of a3 and b3, right? So that's why we could swap this whole prefix and it would still be a valid way. So basically when we do this swapping of prefix, it multiplies our total number of answers by 2. Okay, so what do we have here? We have initial number of solutions, initial answer is equal to 2, because at least two solutions are there, right? Observation 1 and 2 showed us that at least two solutions are there, at least two solutions are there, and that is the given solution. Now at every position where we have this condition holding, that max of ai bi is less than equal to min of ai plus 1 bi plus 1, then that means we can swap this whole prefix, right? We can swap this prefix, we can swap this prefix, and it's also a valid solution. So for every position I such that max of ai comma bi is less than equal to min of ai plus 1 bi plus 1, then we have two options, right? We get two options, to swap or not to swap, right? We get two options, swap or not swap here, swap or not swap, right? Similarly, if we go onwards, if we go to the next step, we consider this prefix. Again, if you see here also max is less than min, here also max of this is less than min of this. So again we get another option is swap this whole thing or not. Okay, so the other option is swap this whole thing or not, swap or not. Again we get another option, right? So here also we get an option. Now if you observe, here we won't get an option, here also we won't get an option. So basically we have two places where we can choose to swap or not. So for each position I, such that it's possible to swap that prefix, right? Max of I is less than min of I. What we will do is we'll double the answer. Why? Because they're all independent choices, whether to swap here or not, whether to swap here or not. And that doubles the number of final options that we get, right? So we can do answer times equals 2. Okay, so if for all position I such that this condition holds, we can double the answer. Okay, and then finally that's it. We can just print the answer directly after this. And it basically just took some observations that an answer is always possible. If an answer is always possible, the array A can be put with all the smallest values and array B can be put with all the larger values. Now when we go through this array, we can only do swaps if this condition holds, right? We can only do swaps if this condition holds. And then when we do this, we can swap the whole prefix. So that gives us two options. Each time we can do it. So we multiply the answer by 2. So let me just show you the code for this. Maybe it will clear it up a bit. So we have two vectors A and B. We take input for them. Answer is initially set to 2. For each I from I1 to n, if A of I, B of I, the minimum is greater than the maximum of previous ones. So here, instead of writing I plus 1, I wrote I. So we can just, if you want, I can just change that. So I'll just say I minus 1, I minus 1. And here I'll just write A of I, B of I. Okay, B of I. So now the condition is the same condition. I just moved I back. That's all. So yeah, min of A of I, B of I is greater than equal to max of A of I minus 1, B of I minus 1. So as long as this condition holds, we can double the answer. Why are we doubling the answer? Because now we got a new place to swap, right? We got a doubling the answer because doubling the answer to signify that we can either swap at this position or not, to either swap here or not, and we have the option to do that, right? We can choose to do that or not. So basically for all the i's where we can swap, let's say we can swap I, and for all the positions, let's say if we can swap for positions I1, I2, I3, IN, right? So that means that each of these gives us two choices, this gives us two choices, this gives us two choices. So basically 2 to the power number of choices, right? Number of choices multiplied by 2. So the initial answer is 2. and then we have to find 2 to the power number of choices, right, which where we can swap. So that's all. For each value, each position where we can swap, we have two choices. We multiply answer by 2 and we take modulo, and finally we print the final answer. So that's all. No DP required. Simple combinatoric solution. Yeah. So let me just show you the an example for this. So let's say, okay, so let me show you an example for observation one, and then I'll show you an example for the whole thing as well, right? So let us take an example. So let's say we have an array like 1 1 1 2 3 3, okay, and then I have 1 2 3 4 5 6. So let's say this is my array A, okay, this is my array A, and then this is my array B. Okay, this is my array A, this is my array B, and this is the example I'm going to show you the whole procedure on. Fine. Now the first thing we need to do is just make sure that one solution exists. We already know that from the input the one solution exists, right? And how do we find that one solution? It's simple. Let's say we choose A to be the smaller one, then obviously, like as you can see, this is in ascending order, this is in ascending order, but as you can see here, this stops being in ascending order, right? And our solution is simple. If we just swap the smaller ones here, right, if we just swap the smaller ones here, then we would have a valid solution, right? A would be equal to 1 1 1 2, and then we take the smaller one here as well, so 3 and 3, right? So each time if we move the smaller one, then A will be sorted in ascending order. Similarly, if we swap like that for B, we would get 2 3 4 5 6, right? So that's what I'm saying. If you can swap the smaller one up, because see, this is smaller, right? Suddenly this becomes smaller, so all the previous values also will be made smaller. That's all. So that's why if we start with the smaller value, all the rest of the values can also be chosen smaller, and we will have a valid solution, right? So now this is a valid solution. Now within this solution, we want to check where it is acceptable to swap, right? We want to check whether it is acceptable to swap. Now here 1 1 it is acceptable to swap. Why? Because max of 1 1 is less than min of 1 2, right? It's less than min of 1 2, so it's acceptable to swap. It doesn't make a difference whether we write 1 1 like this or whether we write 1 1 like this, right? So that's why this gives us two new choices. Okay, this gives us two new choices. Here it's not acceptable to swap because if you take min of this, that's 1, max of this is 2, so it's not less. If we swap it over here, 2 1, this will be fine, but this will become an error, right? This will become an error. That's why we cannot swap here. Similarly, we cannot swap here. We will not be able to swap here, and here also we won't be able to swap. So in this example there's only one swap, and so the initial answer is 2, it gets multiplied by 2, and the final answer will be 4, right? So the answer to this test case is 4. So that's an example of basically what I'm talking about. So I hope you got the intuition. Can you explain why the initial answer is 2? Okay, why is the initial answer 2? Let me just tell you. So the initial answer is 2 because see, we know that one solution exists, right? One solution is like this, right? One solution is like this, and the other solution is, so the other solution will be if we swap the whole array. Okay, so this is one solution, and then the second solution which always will be there is if we swap the whole array. Okay, swap all values. So we, instead of A being the smaller one, A will be the larger one. Okay, so we can get A equals 1 2 3 4 5 6, and B equals 1 1 1 2 3 3. And the reason if we swap all the values is that if this was already in ascending and this was already in ascending, now the new arrays will also be in ascending. So that's why always there will be two solutions. That's why our base case is ans is equal to 2, right? Because always there are two solutions, right? Yeah, there is a DP solution, and the DP solution is basically If we know the number of ways for dp of I, then to calculate the next, we just need to know whether we swap the current position and the previous position or not, right? But if you write the dp solution down, you will get this formula directly. If you sit down and write the dp solution, that's why I was very surprised to see that people use the dp solution, because once you start thinking about dp solution, you will realize this very quickly, that the only reason when where swap is happening is when this is happening, right? The only reason when swap happens is when this happens. So when you write the dp solution down, you should realize this, I guess. But yeah, if you only know dp, then yeah, I can see why you would tunnel vision. But yeah, it's a very simple question, I think. All right, then I hope there are not more doubts on this. If you did not get it, then please rewatch this video, go through the solution, work it on pen and paper, because these solutions require some intuition. Intuition cannot be built by watching videos. Intuition has to be built by using pen and paper and thinking about examples, thinking about 10, 20 examples. Then you'll understand the pattern, right? Why this works. So do try it. Anyways, we'll move on to problem D now. The question which I think most people did not solve today, problem D, and I'll get into the explanation right now. So right after a short 2 minute break, I'll get into the logic for problem D. Right. So I'll just take a break of 2 minutes and I'll be right back. Okay. All right, guys, I'm back, and now we can get on to problem D. So I hope everyone is ready to move on to problem D. 7k people solved C and everyone has DP solution. Yeah, that is a bit weird, because to be honest, I don't see why, if you did a DP solution, why would you not think of the much simpler greedy solution? Um yeah, anyways. So let's go to problem D. Look, do not pay too much mind to all this, cheating, chat gpt, llm stuff. The thing is, nowadays it's so easily accessible that um, whoever uses it is causing harm to themselves itself, right? They're the ones who are not learning skills, while other people are learning skills. The rating itself doesn't matter. The rating is just an indicator of skill. All this will do is just remove the value of rating, that's all, right? So let's not worry about that too much. Okay, so let's move on to problem D. The problem says price tags. So you're the owner of a store. You have n different items. Each item, ith item costs CI coins. We can hold a sale in the format. We divided all prices x times. So this means we choose a common coefficient x, and during the sale, the ith item will cost CI divided by x coins. Where we're taking ceiling, okay? We're taking ceiling. So rounding up. To avoid confusion amongst customers, we pin the new price tags with new prices on all items. But printing new price tags is costly. Specifically, each price tag will cost you Y coins. So you had a brilliant idea. Why not use the existing price tags and simply repin them on other items? Yeah. So there remains one last question. How much should you reduce the prices, or what x should you choose? The x should be greater than 1 such that total income is maximized. Okay, so x should be greater than 1 such that total income is maximized. Total income equals total value of items minus the cost of printed price tags. Determine the maximum total possible income. So the question is a bit complicated. If you didn't read the question during contest, definitely read it, because yeah, it's a bit complicated. Okay. Anyways, so let's try to break down the question. Although one more thing you need to note about the test cases is the fact that there are only 10 test cases, and there's no constraint on sum of n over all test cases. Okay, so be careful over here. This does tell us that there might be some amount of pre-computation going to the problem. Yeah, because there are only 10 test cases and n goes up to 10 power 5. So essentially, basically, n goes up to 10 power 6 over here, right? N goes up to 10 power 6, and we need to solve it using that as our constraint. Okay, so let's just write it. Constraints. um so two things: t goes up to 10, and no n goes up to 2 times 10 power 5. No constraint on sum of n. No constraint on sum of n. So basically, therefore, basically, um, it's the same as n going up to 10 power 6, right? And there being no test. If there's only one test case, then it's like one big test case of 10 power 6, basically. Okay. Now, to break down the problem, we basically need to try um, find the minimum value of x. Find the minimum value of x. Minimum value of x such that um, if the old value of coin of if the old value of the item was ci, let's say the old values were c1, c2, c3, c4, c5, right? Then the new values of these items will be c1 divided by x ceiling, c2 divided by x ceiling, c3 divided by x ceiling, and so on, right? These would be the new values of the items. Yeah, right. And the thing is, if these new values of the items, they require a new name tag. If they require a new name tag, then we are going to have a loss of y coins. We're going to have a loss of y coins. So let's say this required a new name tag, then there would be a loss of y coins. Similarly, there would be a loss of y coins here, maybe here. So every time, let's say there was a new name tag required, new name tag, right? So there was nothing of that old price which could take its place, so we'd require a new name tag. So for each of them which require a new name tag, we would take a minus y. Okay, we would take a minus y. Yeah, it was binary search. No, it was actually not that hard. It's more about clever brute force. Okay, so it's very clever brute force. So yeah, so I'll get into the solution because it's a bit hard to tell the exact intuition. So I'll just tell you some of my intuitions. Okay, so my intuition was um first thing I thought was clearly you cannot binary search, right? You cannot binary search. You cannot binary search. Why we cannot binary search? It's simple because x cannot be monotonic, right? X which gives us minimum, x which gives us the minimum may not be monotonic. May not be monotonic, right? May not be monotonic. Like there's no reason for it to monotonic because the price tags depend on the distribution of the costs of these coins, of these items. So the distribution, if it changes, then the monotonicity will not hold, right? It does not depend on whether which x gives us the optimal answer. It just depends on which price tags we already had, which we can use. So that you cannot predict with binary search. Binary search is not a continuous function, right? So So you cannot binary search because the x which gives us minimum is not monotonic, not monotonic. Okay, because the price tags are essentially random. Like the price tags we already have are kind of random, are kind of random distribution, right? So that's why I quickly realized that obviously binary search cannot be used, right? So no binary search. Usually in these kinds of optimization problems binary search is used, but yeah, obviously we cannot use it here. Okay, what next? So one more observation which we can make is, um, the cost goes up to only 2 times 10 to the power 5. Okay, so this is a very helpful one. Another helpful constraint is that the cost goes up to 2 times 10 power 5, right? So with this we have some good things which we can do. One good thing we can do is maintain a frequency array, right? One thing we can do is maintain frequency array. Why are we doing this? We don't know yet. We just think it might be useful, right? So for each C of I, we can count how many tickets have that cost. Sorry, how many items have that cost, not tickets. Yeah, how many corresponding price C of I are there for items, right? So we can maintain a frequency array for uh, each cost to number of items with that cost, right? Items which had that cost, which had that cost. And we're just doing it for now because 10 power 5 is just big of n itself, and we can maintain that frequency array. Fine. Now what else do we want to do? We want to think of brute force approaches, because we know it's not monotonic, and dp will also not work because it does not have optimal substructure, right? So if you have studied dp, you know that you need some kind of optimal substructure, and this does not seem to have optimal substructure because again the tickets seem to be distributed kind of randomly. Sorry, the costs of the items, the tags seem to be distributed kind of randomly, so we can't really do dp either. So when dp fails, binary search fails. Greedy doesn't seem to be there's no way to greedy x over here. That doesn't even make sense. Like, how will you greedily find the value of x, right? We just need to choose an x. So then we're only left with one option, which is brute force all values of x. Fine. And the only reason we're thinking of this is because everything else failed. dp failed, greedy failed, binary search failed. So we're going to brute force all the values of x in some efficient manner. Okay, all the values of x. How many values of x are there again? As you can see, 2 times 10 power 5 values of x are there. So we're going to brute force all these values of x. Okay, all the values of x. um, yeah, because there's no point of it being more than 2 times 10 power 5, because the coefficient x, if we make it more than 2 times 10 power 5, then everything will have a cost of 1, right? So nothing changes. So basically we need to brute force all the values of x for x goes from 2, right? X must be greater than 1. So x goes from 2 till 2 times 10 power 5, right? So we brute force all the values of x here. Fine. So this much is clear why I thought of this logic of doing brute force, right? Okay, but how do we do brute force? If you do a naive brute force, it will obviously be big of n squared and it will not work, right? So how do we do a brute force here? So let me try one brute force for you, the naive brute force. Naive brute force, I'll write down. Naive brute force. um for every x, in 2 till 2 times 10 power 5, um for every item of cost ci, also we'll keep track of the total cost. Okay, so total cost initially is 0. Total cost is initially 0 for this x, right? So now for every item with cost ci, so now the new cost of this item will be ci divided by x, right? So total cost or total profit, whatever you can say, total profit. So total profit will be equal to ci divided by x, right? Ci divided by x. And we also need to know how many tags we can use, right? So since we already held a frequency array, we had a frequency array. We want to see if this tag of this cost, right, if the tag of this cost is available, right? If the tag of this cost is available, so what we'll do is, if frequency of this tag, right? So if, let's say we had a frequency array, so if this frequency of this value ci by x, right, if this is there in frequency map, right, then what we can do is frequency minus minus this thing minus minus, and then we don't need to do anything. Otherwise we have to do total profit minus equal to y, because we are using a new tag. Okay, we're using a new tag. So this is a valid brute force which runs in big O of n squared. Okay, this is a valid brute force which runs in big O of n squared, right? Yeah. And why does it run in big O of n squared? Because simply because as you can see, what it's doing is, for every value of x it's trying to see, for every cost, what becomes the new value of cost. We're adding that to total profit. Then if the frequency map has this particular tag already, then we can just use the tag. So one tag gets used up and we can do minus minus. Otherwise we need to create a new tag, so we subtract y, that is the cost of making a tag. Okay, and then finally answer will be equal to the maximum total profit, right? So answer will be equal to maximum of ans and total profit. So at the end of this whole loop we can print the maximum answer we got. Okay, and then return ans, right? So this is the naive brute force, and the time complexity of this is, so this is big O of n, this part is big O of n, this is big O of n, and this is also big O of n, you could say, because it's going from 2 to 10, 2 times 10 power 5. So the total time complexity for this is big O of n squared, right? So I hope everyone understood this naive solution, right? Did everyone get the naive solution, guys? So the people who are following this, I can see some amount of people are watching, right? Just a pupil now, Shreyash, etc., etc. So I hope you guys understood the naive brute force solution right now. Okay, so now how do we improve on this, right? How do we make this n log n? Okay, how do we make this big O of n log n, right? And there is a easy observation we can, not an easy observation, pretty hard observation actually. There's a pretty hard observation, or clever observation, right? Clever observation is that, instead of checking for the values of CO5 and then calculating the value of CO5 divided by x, we are going to check for all the possible values of CO5 divided by x. Okay, so all the possible values of CO5 divided by x, we're going to check that, and we're going to compare that to how many items are there. So let me just make it clear. So the first thing will be same for every x. For every x in 2 times 10 power 5. Okay, and then what we're going to do is, yeah, so total profit will also be like that itself. Total profit will also be like this itself. Now what we're going to do is, we're going to try for every new cost. Okay, for every new cost. And what are the possible new costs of an item? So every new cost can be in like 1, 2, 3, like these are the possible new costs, all the way up to 2 times 10 power 5 divided by x. Okay, so these are the possible values of new cost. Okay, so what is new cost? New cost is basically this. Okay, so this is the, you could say, new cost, right? Old cost is c of I, new cost is c of I divided by x. So this is the new cost, right? So for every possible value of the new cost, we will try to find how many such c of I were there. Okay, so every possible value of new cost, we will try to find the count of how many such c of I were there. Fine. So every possible value of, from every value of new cost, we will count. So we will do, so let me just write this bit more neatly. Let's just say for every value of new cost in 1 till 1 till 2 times 10 power 5 divided by x, right? So ceiling. So every possible value of new cost here, what we're going to do for this is, we're going to see, find the count of, find the count of c of I, which give this, which give this um which give this new cost. Okay, new cost when divided by x, when divided by x. All right, so we need to find basically how many c of I are there which give this new cost. And let's say we have some fast way of finding this count. Okay, let's say we can find this count quickly. Let's say we can find this quickly. I'll explain how to find this quickly later, but let's say we can find this quickly. Then what we will do is, um then what we can do is, we can do the similar process but like in reverse, right? So for each of these counts, we need to add the c of I divided by x. So for, we can add total profit, total profit can be added with the number of elements which give this value. So count times new cost, right? So I hope you guys are following. This new cost is nothing but the c of I divided by x, right? Which is the new cost which we get by when we divide the cost c of I by x, right? And what we're saying is, instead of checking for each c of I and then finding the new cost and then adding that to total profit, we're going to iterate over all the possible values of c of I divided by x and find how many c of I are there which give us this c of I divided by x, right? And that's why total profit will increase by count times new cost. Okay, so that's why we're increasing total profit by count times new cost. And then we need to find how many, how many tickets to buy, right? How many tickets to buy. So that is simply equal to, so if, how many not tickets, how many tags to buy, right? How many tags to buy. So if the frequency, right, if the frequency of this new cost, let me just call it new cost, right? If this frequency of new cost is greater than or equal to count, then we don't need to buy any tags, right? If we don't need to buy any tags, if we have enough tags for this cost. Otherwise, if it is less than the count, it is less than the count, then we need to buy tags, right? So then how many tags do we need to buy? Total profit will be subtracted with y times count minus frequency. Okay, so this is the number of tags we need to buy, so we'll just subtract the total profit with that. Okay, let me just write it neatly. Total profit will be minus equal to count times y times count minus frequency of the new cost. Okay, frequency. So I'm just writing it frequency for short. Please understand, this means frequency of new cost. Okay, so for um every additional tag that we need, we're multiplying y with that and subtracting that from total profit. Okay, so right now I have not explained how we are finding the count, right? So we need to figure out how to do this, but for now everything else I hope you understood. What I'm saying is, we'll try every x and we'll try every value of the new cost, right? So the new cost can be from 1 to this ceiling of 2 times 10 power 5 divided by x. We'll find the count of c of I which gives this new cost. Total profit will be this count times the new cost. And also how many new tags we need to buy. The number of new tags we need to buy is simply, if we have enough tags, that is the frequency is greater than or equal to count, then we don't need to buy any tags. But if we need to buy new tags, it will simply be um, count minus frequency of this. So we're subtracting y times that from total profit. Okay, so I hope you understand this. And let's say we can find the count of C of I in O of 1. So just trust me on this. We can find the count of C of I in O of 1. Just trust me on that. So then what would be the time complexity of this loop, right? You might think it's still n squared, because instead of looping over the costs, we're simply looping over the possible divisors of the cost, like the possible number of costs divided by x. But actually it is much lesser. Why is it lesser? Because um, for x equals to inner loop does 2 times 10 power 5 divided by 2 iterations. For x equals 3, we get 2 times 10 power 5 divided by 3 iterations. For x equals 4, the inner loop will do 2 times 10 power 5 divided by 4 iterations. Similarly, x equals 5, 2 times 10 power 5 divided by 5, and so on. And as you can see, this is the classic geometric series, which is bounded by so I'm not sure if you would know this. So yeah, you have to do some like 1600, 1700 level problems to even see this idea. But basically the idea is that um, if you have n plus n by 2 plus n by 3 plus n by 4 plus n by 5 plus n by 6, so on, right? Big O of this is equal to big O of n log n, right? So the time complexity of these two loops will just be big O of n log n. Okay, because the possible number of um, new cost values, the possible number of new cost values keeps decreasing very fast. That's why the inner loop does not take n square, it just takes big O of n times log n. Okay, so are you guys following this? Yeah, I'm not sure the name of the series. I just call it geometric. It's called Hamilton series. Okay, so I guess if the name is Hamilton series, I believe you on that. I'm not sure, but yeah, the time complexity of this is, it's a well-known trick that the time complexity will be n log n itself, right? We are basically finding how many possible divisors can give you the correct cost, and that's why we are only iterating through n by 2, n by 3, so on. So the time complexity is n log n. Okay, now how to quickly find the cost of Ci, right? How to find the count of Ci, right? How to find the count of Ci, and that's also very simple. So we already have frequency array of Ci, right? We have frequency array of Ci. Why do we have that? Because simply Ci can only go up to 2 times 10 power 5, so we can make a frequency array for it, right? We have frequency array for Ci. Now in a given range LR, we need to find total count, right? We need to find count of Ci. So for that we can simply use prefix sums. Okay, we can simply use we can simply use um, we can simply make prefix sum of our frequency array. Okay, make prefix sum of our frequency array, and basically what we can say is prefix of R minus prefix of L minus 1 is equal to the count. Okay, and we can do this obviously in big O of 1 if you know prefix sums. The time complexity for this is just like after the pre-processing, which is big O of n. To answer a query, it's big O of 1 in prefix sums, right? And basically what is the prefix sum storing? The prefix sum is storing the fact that between cost Ci equals L till cost Ci equals R, how many items are there? Okay, so that's what the prefix sum is telling us quickly, right? How many items are there such that its cost goes from the range L to R. Now what is our L and R? Our NLR is simply the values which give, what is LNR? What is LNR? It is simply the values. It is simply the first and last values. The first and last values of Ci, which give us, which give ceiling of Ci divided by x is equal to the new cost, right? So basically we're iterating over the possible new cost, right? For every new cost between 1 to this, we're finding the count of Ci which give this new cost, right? So we can find that which value first gives ceiling of Ci divided by x, and which is the last value which gives ceiling of Ci divided by x. Then we can find the count of this Ci using that prefix sum array. Okay, we did a prefix sum on the frequency array. So we can simply find the LNR and we can find the new cost. If you want explicit mathematical formula of LNR, so for a given x and new count, let's just call new count NC over here. Okay, NC. We know that NC equals C of I divided by x, right? So what is the smallest C of I? What is the smallest C of I satisfying this? That is simply that will simply be x minus 1 times the new count plus 1. And what is the largest C of I satisfying this? That will simply be x times C of I, x times new count. Okay, so this is the smallest C of I satisfying largest C of I. We're finding how many total items are there between this cost ranges, right? So smallest cost, smallest old cost, and this is the largest old cost, which gives us C of I when you divide by x. Okay, so in this entire range, we're just taking prefix sums and we're finding the count. Okay, so let's do a quick summary. What is our summary? Basically what we're doing is, for every x, right, let's just compare with the brute force. What did we do in the brute force? For every x, for every item, we added the total profit. Here, for every x, for every new cost, we are finding how many items give us this new cost. How are we finding these items? We are just saying that the smallest old cost to give this new cost is this, the largest old cost to give this new cost is this. So since we have done prefix sums on the frequency array, we can find how many count of old items which give us this new cost. Then the total profit can increase by count times new cost. And if we don't have enough tags, we can subtract by y times count minus the frequency of this tag. Okay, so that's it. And then once this loop ends, the time complexity of this loop we have shown is this sum, which is equal to big O of n log n, right? So the overall time complexity, let's just write it down. Overall time complexity, n equals number of elements. Okay, t equals test cases, and let c max equals max value of C of I. So this goes up to 2 times 10 power 5, right? And this goes up to 10, and this goes up to 2 times 10 power 5 again. So our whole time complexity is big O of t. Here the time complexity of t will be multiplied. Okay, so time complexity big O of t times. So first we need to make the prefix sum array, right? We need to take the input. We need to make the prefix sum array. So take the input, make the prefix sum array C max. Now after that, we need to do this n log n type of logic. So for every value of x, so all the values of x go up to Ci, and every value of new cost. So we'll get plus Ci, C max log C max, right? So we get C max log C max. All right. And that's about it. This is the time complexity. You can simplify it to big O of t times n log n. Since n and C max have the same max bound, we're just simplifying it like this. So this is the simplified version, Tn log n, right? Let's have a quick look at the code for this. Yeah, it is harmonic series, yes. That's pretty much what I said. Is character extension accurate? No, sometimes it's wrong, but roughly within 10 points it's correct. Okay. So for problem D, let's have a look at the code. I'm taking in n and y, taking in the vector v, and I'm making a prefix array, right? So instead of having both a frequency and a prefix array, I just have one array, which is my prefix array. Okay. Because using a prefix array, you can get the frequency array back. You just need to do prefix of I minus prefix of I minus 1, right? So for every I, I'm taking the input and I'm increasing in my frequency array. Now I do prefix sums on it in this line. Okay, I do prefix sums in this line. Now initially my answer is set to negative infinity for each value of x. So brute force all values of x. Brute force all values of x. Now here what I'm doing, um, brute force all values of new cost. Okay, so new cost here I'm just writing as I, variable I. Okay, so it's the I variable itself. L and R is basically, like I said, the bounds of old cost which could have given us this new cost, right? So what are the old costs which could have given us this new cost? This is the L and this is the R. Same exact formula you can see, L and R. And the only thing I've done is R is equal to min of this n max. Is it min of n max? Because I don't want to access some value outside of my prefix sum, right? I don't want to access some value which is beyond the boundary of my prefix sum. That's why I just took a min over here to make sure that it's between, like it does not do invalid memory access. I don't want invalid memory access. That's why I took a min over here. That's all. Now I need to count the elements in the range. So prefix of r minus prefix of l minus 1, right? Simple. I'm counting the elements. The cost increases by this count, right? Cost increases by new cost times this count, right? Where is it? Yeah. The total profit increases by new count times new cost. Same thing. This is my total profit. Okay. This is the variable I call total profit. Okay. Now I'm writing as cost over here. So total profit will increase by this much. Now I'm calculating how many tags I need, right? So my logic for tags was basically, um, if the frequency is less than the count, then the total profit equals y times count minus frequency. So same thing I've done, but I've just written in one liner. Max from 0 versus this is count minus frequency. And to find frequency, since I'm only storing prefix array, I just need prefix of I minus prefix of I minus 1. So this is basically count minus frequency itself. Okay. If frequency is less than the count. Okay. So yeah, that's what is tags needed. Now for each tag which is needed, I'm subtracting y times that value, right? For each tag, you need to pay a cost of y. So I'm subtracting y times tags needed. And then my answer is simply max of answer and cost. And I finally print. Oh, if once we have checked all the possible values of x, we have done brute force, I print my final answer. So even though this question was pretty daunting, it turned out to be just math of the harmonic series and a brute force. So math, brute force, and harmonic series, right? And prefix sum. So you could say the topics for this. Topics are math, harmonic series idea, right? Series idea, brute force, and prefix sum. So yeah, pretty nice question. I think not very standard, but yeah, pretty cute question. I think, right? So that's the solution. Any doubts? Please put it in the chat. We are discussing only up to D. So yeah, we have done all the discussions. So any doubts regarding the questions or any general doubts you can ask now. Any doubts, guys? No doubts? Okay, then, since there are no doubts, okay, since there are no doubts regarding the questions, we'll be ending the session now. Thank you everyone for watching. Hope you learned something. If you find any part confusing, then please go through the code, use pen and paper to try out the examples, rewatch the sections of the video, because a lot of times this is based on intuition. Intuition just doesn't come from hearing it once. You need to hear it a few times, and you need to think about it. Any hint for even? I genuinely don't know. Actually, I tried. It's obviously some kind of DP, but I'm not able to solve it yet. Like, uh, almost 1 hour of the contest I spent on it, and it is some kind of brute force slash DP idea. But yeah, I was not able to find how to do the transition for the DP in even. So I won't comment on even. I guess we'll have to wait for the editorial. All right then, guys. Hope you learned something. Do check out Eliminators course once again. Right, the self-paced courses are live, so if you haven't checked them out, and if you want a systematic way of tackling your competitive programming, go check them out. Right. Good night, and see you in the next PCD.